Okay, it's 9. Good morning, everybody. Today is a day dedicated to machine learning at the Escape Summer School. And we start this morning with Martino Sorbaros, who will do the first part. So thanks, Martino, and the floor is yours now.
Thank you, Thomas. Welcome, everyone. I'm Martino Sorbaro from ETH Zurich, currently in Italy. Apologies if there's any noise around me, first of all, but I hope you don't hear it. So this is the introduction to machine learning tutorial for the morning and again in the afternoon. First of all, I would like to thank those who designed this workshop with me, who are Benson Muite and Claudia Bedaites. Claudia is also going to teach this afternoon. And the materials that I used, these slides and some of the code that we will be looking at later today are also based on pre-existing materials. The slides are partly by my friend Maria Stefanoe from ITU Copenhagen. And some of the code comes from a machine learning and statistics class of UC Irvine, which is excellent. And I recommend everyone, if you want a bit more in depth or look at other topics in machine learning, that's a good place to start at, especially for physicists and astronomers. So what are we going to talk about today? How is it going to be structured? In the morning with myself, I will first do an introduction, about 45 minutes, which is going to be these slides that you're seeing right now. And then we will start looking into Scikit-learn code. So Scikit-learn is the library for machine learning in Python. There's going to be a coffee break, I think, at 10:30. And then there's going to be a second tutorial on dimensionality reduction and supervised classification. In the afternoon, it's going to be Claudia teaching, and she will talk about model validation and regression methods. As far as I understand, the lecture tomorrow about deep learning is canceled. So I'm sorry about that, because deep learning is always the most important part and maybe the one that you guys were looking forward to the most. But you will find plenty of materials, of course, if you're interested. So from the questionnaires that the school has sent around, I saw that machine learning was one of the topics people attending were least familiar with. So I'm going to start really from the beginning and ask, what is machine learning? Let's think for a moment about how the world of computing has changed in the past few decades. There were big differences, I would say, in 3 directions at least. The first is the amount of data that is available. We went from megabytes and gigabytes, perhaps, to easily terabytes and even petabytes and exabytes if you are a big data company. These are scales of data that personally I can't even imagine properly. And the amount of data available, the change is not just a technological change, it's also a societal change, right? These data are available because we are so much more connected. Everything is connected to the internet, everything is digitized, so it's a lot easier to collect things from all aspects of life. The second direction is the speed and compute power available in terms of speed of processors, in terms of amount of operations we can do per second, and in terms of amount of data that we can send per second. Of course, computers have become a lot more powerful. This is well known. And now, even if processors have kind of stopped becoming faster, not as much at least, still we have data centers and computing centers which are still growing a lot. The third direction of evolution is in the algorithms. So we have new ideas, new models. Mathematicians and computer scientists have come together and have designed new ways to deal with data, new ways to simulate. And you may be tempted to think that this is where machine learning comes from. In part, it's true. But in fact, the big success of machine learning and of artificial intelligence, which is how it's also called. It's not really the same thing. Artificial intelligence is bigger than machine learning. Machine learning is a subset of artificial intelligence. So I would say that the current boom of artificial intelligence comes from all three of these things. Because, of course, yeah, there was a lot of research in the algorithms. But some algorithms, like, for example, the basics of neural networks, were already well known in the 60s. And what really enabled their success right now is the fact that we really have a lot of data to train them, and we have the computing power to deal with these data. So all three of these aspects have really generated the current boom of machine learning usage. But I haven't really answered the question of what is machine learning. A machine learning algorithm is an algorithm that is able to learn from example, so to change itself in a flexible way, starting from data. Why do we need that? So think of a task like I have to recognize a cat in a picture. I don't know how to explicitly tell a computer how to do that. So the point of machine learning is telling the computer to do something without explicitly programming to do so, but instead learning from data, from its experience, and its experience is the data. So I was talking about recognizing a cat. Think about it yourself. How would you say that you recognize a cat? I show you a cat and explain to me what makes you think that this is a cat. You may tell me something like, oh, it has whiskers, it has fur, it is of a certain size, and all these things. And of course you would be right, but then I can still ask you, how do you know it has whiskers? How do you know it has fur? And all these things. So you could always, the real question here is, how do you go from photons that hit your eyes in a certain pattern to the understanding that this is a cat? The brain does this in an extremely complicated way. And the question really is, even if we do it every instant, we don't know how to explain how we do it, right? In a logical way. We don't have an algorithm. So it's not really logical thought. It's not conscious thought. So in the same way, we don't know how to explain to a computer, this is how you recognize a cat. It's difficult because you have to go from a representation of pixels, which are a bunch of numbers, because every number tells you the color of every pixel, of course, but the representation is a bunch of numbers. And you have to go to a concept, which is cat. And the thing is that the concept of cat varies a lot. So this is a cat, and it's just orange and blue. This is a cat, and is of completely different colors. These are also cats, and the pixel representation of this and the pixel representation of this have really, really nothing to do with each other. However, they both share the concept of cat, but it's such a high level that it's very difficult to teach it consistently. So what you do if you want to do this on a computer is you show an algorithm a lot of pictures of cats and hope that the algorithm figures it out. So that's the point of machine learning. It's about automatically finding the relevant features in data, which could be images, but it could be many other things. Automatically find them so that you don't have to tell the computer, this is what you should look at, because we don't know. In slightly more mathematical terms, essentially, we have what you want to learn is a function, a predictive function that maps the input data into a prediction. And we will look now in the rest of this lecture, we will look a bit more about how this data might look like, how this prediction might look like. And what the model looks like is the subject of the tutorials. So we have a sort of magic box, which looks at things like input-output pairs. So we have examples. These are the data that we train on, the so-called training set. Training set is an expression that we will use a lot. which could be something like input-output pairs. So we have an input data like the image of the cat, and we have the output, which is cat. So the concept of cat. So that's the desired output. Or we could also have a case where we only have input data, and the task is to find structure in them without an explicit need for that specific output. But importantly, usually, for most machine learning tasks, you have a way of evaluating whether the model is performing well or not. And this is the error function, which is a function of the output of our model, and tells us the model is doing well, the model is not doing well. So what really learning is about is we have a function that goes from data to an answer to our question. And this function depends on a bunch of parameters. So it has the input data, so f of d, but I haven't written it here, but it also depends on a very large bunch of parameters usually. And the objective of machine learning is finding out the correct value of parameters so that in this large family of possible predictor functions, we find the right predictor that gives us the solution to our problem. How do we find the right value of the parameters? We have the error function. And so we optimize this error function by changing these parameters in a way that minimizes the error. The error function can also be called loss, fitness, negative log likelihood. There are many ways of talking about it. I would usually call it loss. And so, yeah, so essentially, it's usually an optimization problem. I can maybe stop for questions if there are any, Thomas.
Yes, there is already one question, kind of wide question. When did the first machine learning algorithm appear, and what was it for, if you know?
All right. So I'm not an expert in the history of machine learning, but that's a very interesting question, actually. Here, this quotation that I wrote here, the field of study that gives computer the ability to learn without being explicitly programmed, that's 1959. So the use of the term was first popularized around that time. Artificial intelligence in general is an idea that was around for a long time, of course, but for most of its history, it was not necessarily learning intelligence. So there's also artificial intelligence, which is things like automatic theorem proving, kind of like tree search of the truth or falsity of statements. So like it's called logic programming, and that's also artificial intelligence. And it was much more popular back in the days. Learning in itself, the first models of, I can tell you about neural networks because I know a little more than compared to machine learning in general. There were already neural networks in the, at least, so I'd say 50s, there was already something. Actually, the first article that started talking about artificial neurons for logical thought and not for modeling the brain was in 40-something, 46, 47, and it was McCullough and Pitts. It's a very famous paper, which was deeply entrenched in logic. And then there was a lot of research after that. There was a bit of a break, so-called AI winter in the 70s, maybe early 80s, and then there was a boom again when they discovered that they could add more layers to a neural network and train it still. Yeah. Okay, I'm probably taking too much time answering this question, but there's definitely a long history of trying to learn with neural networks. And there's also a large history of artificial intelligence without learning. Starting, it depends what you call artificial intelligence and what you don't, but starting after the war.
Yeah, thank you.
Okay, so let's talk a little bit about types of learning. So essentially what I'm doing here is introducing terminology. You will probably be already familiar with a lot of these things. perhaps not. So I'm going to talk about this. The first distinction that I want to make is between supervised and unsupervised learning. I hope you don't hear this noise. In supervised learning, we have explicit examples of the output. So that's the distinction that I was making earlier. In supervised learning, we know the label that we are supposed to give to a certain input. It could be a numeric label, it could be so we know the desired output. And because we know the desired output, we can really easily compute the accuracy by looking at how close the output was to the desired output, or what is the fraction of correct outputs versus wrong outputs. Within supervised learning, we have both classification tasks and regression tasks. A classification task is where we have the data is divided in 2 or more classes, for example, cats and dogs, and we have to tell the difference between cats and dogs. So the targets, the desired outputs, are categories. In a regression task, as I'm sure you will know, the desired output is numeric. So we have for every input data point, we have a desired output number or multiple output numbers, usually 1. So we have training data, each with their associated number, and then we say, okay, what is the number that should be associated to this other data point? On the other hand, in unsupervised learning, we let the computer learn by itself, which could be things like finding particularly important features of the data, model the underlying structure, reproduce a probability distribution, or categorize the data into classes without knowing what the classes should be. And this last thing that I talked about is called clustering, which is the first example of machine learning we will look at today. And clustering essentially means grouping data into different categories based on their features and on some assumptions, which are hyperparameters of the model. And so we don't have labels, and we just try to group the data based on their features. That's, for example, detecting outliers, seeing how many types of something there are in, but without the help of targets, of labels. I'm going to quickly play a little game with you to give you an example of how supervised classification would work. So supervised classification is in my opinion, is the most common task in machine learning the way we intend it today. But perhaps this is distorted by the fact that it's a very common task in deep learning, so in the use of neural networks. For example, image recognition, it's what deep learning really excels at, and that's the task that I was talking about, telling a cat from a dog, but also from 1,000 different classes. And today, neural networks are really successful at that. They can tell really even the sub-race of dogs better than humans. And that's a classification task. So in the classification task, we start with the training phase. In fact, in most tasks, we would start with the training phase. So we have a training set, which is like this, and includes both images or whatever data we have, which could be also sounds, it could be various kinds of features, a list of features, of measurements. And we also have the expected output, the labels for each sample from the training set. So I'm going to play this little game with you. Try to learn from these. So you are now putting yourself in the role of the machine learning model. I want you to look at these and say, I tell you, these are Georgian alphabet glyphs. So they are letters from a Georgian alphabet, and these are letters from a Tibetan alphabet. And I will ask you to remember this. That's the training phase. And then we move on to the test phase. The test phase consists in this. You are the algorithm, and I ask you, which alphabet does each of these belong to? Is this Tibetan or Georgian? Is this Tibetan or Georgian? And so on. Think about it for a moment, note it down. This is not a difficult task. sometimes I think neural networks have it much harder than this. Okay, so say that you've guessed like this. You've said Tibetan, 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 Georgian, Georgian. The test phase is, now I look at the labels of these. Now, at the beginning, I don't look at the labels. So I have the labels for the test set, but I don't look at them. I feed these to the model, and I ask the model to make a prediction. So this is the prediction. And now I do look at the correct labels, and I compare them. And I find that only this one was wrong. The others were correct. And so, for example, I have the evaluation accuracy. Now, the accuracy is one possible measure of finding whether the model was successful. But in fact, it's not the only one. I may need things like precision and recall, especially when you have unbalanced data sets with a lot more data in one class than the other class. And Claudia is going to talk about model evaluation a lot more in depth in the afternoon. All right, so as I said, this is called the test set. Okay, so far we've talked about supervised versus unsupervised, classification versus regression. I would say these are the main categorizations. And lastly, I want to talk about, but I will only mention it, reinforcement learning. Reinforcement learning is a completely different kind of learning. We are not going to do any reinforcement learning in this school. I would say it's a lot more difficult to deal with reinforcement learning. It's usually considered the third kind of learning after supervised and unsupervised. So we have supervised, unsupervised, and reinforcement. So what's reinforcement learning? Imagine an agent that is exploring a new environment. The best example of this is you're playing a video game. In the video game, you don't know what you're supposed to do. So you have a character that is there somewhere. And you do know how many points you're getting for all the actions you do. Sometimes you get points, sometimes you lose points. Probably you will be able to learn, because usually we don't read the manual of a video game. You just learn by trial and error. So that's the concept. In supervised learning, we learn by example. So we are told, this goes with this goes with this is Georgian, this is Tibetan. In reinforcement learning, we learn by trial and error. We are free to experiment. And then we are told, this was a good choice, this was a bad choice, but that's it. And in fact, this is how we humans learn a lot. We are really made for that. We even have a system in our brain which gives us this sense of reward or punishment. And that is supposed to give us the ability to do reinforcement learning. And this is also how we would train a dog. The dog understands rewards and punishments. We use reinforcement learning whenever we don't have really examples, or whenever we don't have an explicit example of how to solve a problem and we want the model to figure it out. And also whenever we don't have an explicit way of evaluating the result, except by this was right, this was wrong. So maybe this picture is not so easy to understand. What it is it's a car race. So these are lots of examples of cars. You shouldn't imagine them all there at the same time, but they are all different trials of the same algorithm. So the car is supposed to go as fast as possible on this track and not get out of the track. So it gets punished whenever it gets out of the track, and it gets rewarded as the faster it goes. So that's an example of learning from a video game. And the computer has access to the controls, go left, go right, as you would do when you play video game. So with this method, they taught neural networks how to play Atari video games to accuracies better than humans. And also, you may have heard of AlphaGo, or AlphaZero is called now. the DeepMind algorithm that plays Go, this Asian, very difficult game similar to chess, which has a few years ago beaten the world champion. So the reinforcement learning is key for this kind of learning. Okay, so far I've talked about models and ways of learning. I'm aware that I haven't explicitly talked about how these algorithms work and what these algorithms are mathematically. We will look at some of them in the various tutorials. But it's impossible to give a complete overview because each of them works in a different way. So let's talk now. I've talked about models. Now let's talk a bit about data. I will go rather fast on this part. So both the data, D, and the prediction can be of different kinds. They could be categorical data, ordinal data, numeric data, and many other things. But in fact, even an image could be classified as one of these three. You just have a lot of features, one per each pixel, or maybe three per each pixel if you're in color in RGB colors. But we are still talking about numbers essentially. Okay, so categorical variables. A typical categorical variable is the prediction of a classification model. Okay, so you want to tell if something is a cat, a dog, a giraffe, and an elephant. And these are mutually exclusive, and they are not ordered. There's no possibility of mathematical operation or of ordering lesser than, greater than. But you may also have categorical data. An example of that is male, female. So imagine you have a lot of entries, and the examples are data about people. So you may have an entry. One of the features that you have about every person is gender, male, female, or whatever. And these are categories. You can also have ordinal data. So these are also categorized, they are binned, but this time they are comparable. There is an order relationship. And then, of course, you can have numeric data, which are continuous, ordered, and so on. Note that sometimes it's not your choice how these are, if you have categorical, ordinal, or numeric data. And sometimes it's also not intrinsic in what the data is, but rather in the way it was gathered. So examples of this are, suppose that you're working on predicting the wind, the electric power that you get from a wind turbine. You will have categorical variables like the direction of the wind, the type of the turbine, I don't know, the weather perhaps. You also have ordinal data. For example, imagine the capacity of the turbine was recorded not as continuous data, but as different categories. So like binned. And then, of course, you have numeric data that you have at a high precision, like the speed of the wind and the temperature outside. I want to stress, so the reason why I'm talking about this is that some work that everybody will have to do while using machine learning models is about how to pick the data that you're feeding to the model and how to represent it numerically or mathematically before you feed it to the model. So you may need to do some pre-processing and choose the right format. Generally speaking, the best format is the one where you do part of the work as much as possible. So to similar representations, to inputs that are semantically similar for the task, you also have similar representations. But of course, that's not always possible. So think of this example. This is a very, very classic machine learning task that we will also look at today. Handwritten digits. It's called the MNIST handwritten digits dataset. It's a very, very classic example. So you have lots and lots of scans of people handwriting the numbers from 0 to 9. Of course, there are lots of ways of handwriting them. And as I was saying earlier, the correspondence between pixel and number is not necessarily that obvious. For cats, it's a lot harder, of course, but this is also not obvious. Now, the problem of the pixel representation is that each pixel is a separate attribute. So again, this is a bunch of numbers. For example, 400 features. I'm going to use the word features to talk about the dimensionality of the input of every single input, of every single data point. In this case, if we have a 20 by 20 image, then it's going to be 400 features or attributes, which are real numbers. So I was saying, the problem of the pixel representation is that even if I translate by 1 pixel the whole image, the 6 is still a 6. Okay? The concept of sixiness and zeroness, so the semantic aspect, is completely invariant with respect to a translation by 1 pixel or 3 pixels. Okay? But the pixel representation is really not. If I change by 1 pixel, my vector, my array of data, is going to be completely different, because it doesn't have a concept of these 2 pixels are adjacent. It just knows 400 dimensions. So we have a problem in this case, and this problem is solved by making the model itself invariant for translations. And that's the case of convolutional neural networks, for example, if you've heard of them. Another example is we are working with text. How do we represent text numerically? This is a whole subfield of machine learning, natural language processing, which is huge. It's also not my field. So if we have a string of characters, which is our text, how do we represent it? One way of representing it is character level. Each character corresponds to a vector in a relatively low dimensional space, because we are only telling characters apart. And then our input would be a sequence of these vectors. But again, we have the same problem. As soon as we remove 1 character, the text is essentially the same, but the vector representation is completely different because we shift everything by 1. So that might not be the best way. Another way is we use another machine learning model that takes every word and turns every word into a vector. And we do it also by learning in this part of the algorithm, so that to words that have similar meanings, we associate similar vectors. Now, that's a very smart thing of doing it, but we also have to learn this part, so it's not that easy. And this is called an embedding, by the way, in natural language processing. And maybe if the only thing we are doing is a detection of spam, what perhaps we only need the presence or absence of certain words. We don't even need the sequence of words. So in that case, we just look at the frequencies of words and whether certain words appear or not. And that's a smarter representation if the task is easy enough to be solved in this way. And one last example is music or speech, so sound in general. And in this case, we may be tempted to just sample at intervals our waveform, but that's definitely not the smart thing of doing. The smart thing to do. Something much better is do a Fourier transform in time as well. So at every time point, we know which frequency bands have more energy content, and so we know the pitch or the general frequency space. That gives us a lot more information about what's going on than the waveform itself. So the message of all this was pre-processing the data in a way that is meaningful to the model is very important. I also realized that I said this in a rather vague way. I had to say this, but it's difficult to go into details or to give really hands-on examples, because this is really very task dependent. Pre-processing and dealing with your own data is always going to be very different based on your data. Sometimes the challenge is just even going to be how to read the format that we have this data in and convert it to the right format, how to fill in missing data. These are very practical things which are difficult to cover in general. I'm almost done, but I will stop to see if there are other questions. I'm sorry, I forgot to do it until now.
Thank you. There were a couple of questions. Is there a connection between the error function mentioned and the error function in math? In mathematics.
Oh, you mean like the integral of the...
I suppose that was...
No. So the error function here is a generic name for any function that you use to evaluate your model. So, for example, I mean, the simplest example is the mean squared error. If you're doing a regression task, you compute the squared difference, so like essentially the Euclidean distance between your predictions and the predictions and the expected labels. So you compute the difference, square it, and sum everything. That's the mean squared error. And that kind of gives you simply the distance between the expected result and the result, that the prediction that you got from your model. And you try to align these two. So you're trying to minimize it. So mean squared error is the first example. There are also like binary classification functions which are used for this purpose. There are really a lot of possible functions. But they really depend on your task. It's your way of evaluating, is the model doing well or not? So you define what you want to minimize. Of course, there are certain functions that are easy to minimize mathematically speaking, others that are numerically impossible because they're non-differentiable and so on. But it depends on the task.
Yeah, thanks for the precision. And another more general question, I will read it. Some people argue that since various statistical techniques like Bayesian methods, etc., are already in existence, machine learning is not really necessary. What is the counter-argument for preferring machine learning methods like neural network over other statistical techniques?
That's a nice question. So I think the difference comes when you really have lots and lots of data and very complicated tasks. So if you have the classic task of computer vision, which is, as I already mentioned, is the one that I always go to as an example, which is the ImageNet classification problem. So you have 1,000 classes, some of which are species of dogs. Others are airplanes versus ships versus bicycles versus humans versus houses. So 1,000 of these. And you have millions of images to train on. How do you frame this as a statistical task? So that's where it becomes difficult to talk about. Of course, it's always statistics. We are doing some very sophisticated statistics, but it's very difficult to use the language of statistics when we are doing this. And in fact, there is a lot of research in machine learning, which is very empirical, especially in deep learning, because these models are so large and complicated that sometimes the people who create them don't know exactly how they solved the problem and why they solved the problem. So there's a huge, recently I was reading a very interesting paper of mathematical theory of deep learning. And a lot of questions in these fields are, why does the model even converge? Why does it not get stuck in local minima? Why does it have such an amazing generalization ability? From a few examples, manages to generalize to other things that it has never seen before, for example. in some cases, it's not neural networks, for example, it's not obvious why it even works. For example, why do neural networks not overfit? They have millions and millions of parameters. And there's the famous, I don't know if it was Fermi or who said that if you have two parameters, if you have a sufficiently large number of parameters, you can fit even an elephant and make it wiggle its tail. Okay, so here we are talking about a model that has millions and millions of parameters, and yet it does its task without overfitting and is able to generalize to other things that it has never seen without memorizing. So, this is to say that we are going into a bit of an alchemy side of things, that they become bigger than us, bigger than our statistical theory, even if the foundations are statistics.
Yeah, thanks. I think you are right about the complexity of the machine learning algorithm now compared to statistical methods. Yeah. Thank you.
Okay. So I'm almost at the end. I'm maybe a couple of minutes late. I want to really give you a summary of everything. What do we do? What in practice? What does it mean to train a machine learning model? So this is the pipeline. This is what we do. First of all, we need to define the task. What is it that we want the model to predict or to do in general? So we have to define whether it's a supervised or unsupervised task. Is it a classification task, a regression task, a reinforcement learning task? So the question is, what do we want to do? Let's try to do this by questions. The second point is get the data. So second question is, what do we train this on? Where do we find this information? Where do we learn from? The third one is choose the right representation, which is what I was talking about right now. Perhaps was maybe not that clear, that part, but how do we feed this data to the model? How do we express it mathematically, and so on. 4 is get an overview of how the data looks like. So imagine the person who collected the data for you comes with the data on a hard disk. First of all, you want to plot it, probably. So get an idea of how it looks like, see how many features you have, how many data points you have, which is the dimensionality of your data set. So for example, if there are questionnaires, how many people answered your questionnaire, and how many answers per person you have. So how many questions were asked, how many data features you have per person. 5, prepare the data. So what do we need to do to make this data suitable? If there are missing values, we need to figure out what to do with them. If they are in the wrong format, we need to convert the format. Sometimes we have to clean them of certain kinds of noise, outliers. We may want to apply some transformations, and so on. And then we move on to the actual machine learning part, which is we select a model. We need to figure out what is the right mathematical algorithm that is suited for learning from this data. And I know that I haven't covered this part. But the choices that we make are based on how much data we have, how complex it is, what kind of data we have. And then we can proceed finally, only at point 7, we can proceed to train this model. So we feed the data to it. And we start by evaluating it on the training set. So first we see if it has actually learned the training data. And in this phase, we will want to fine-tune the model. So we will change the properties of this model, perhaps try a different model, change the hyperparameters. I will go into what hyperparameters are in a moment. And then finally, we evaluate it on the test set. The test set is usually some data that we've left aside just to check that our model is generalizing properly. We don't want to train on all of our data. We train on maybe 80% of our data, and we keep some to check that the model is not overfitting, but is able to generalize to data it has never seen before. Once we know this, then we can use the model in production if we are engineers working for a company, or in the real world if, I don't know, depending on what you need to do, right? And at this stage, the model is going to see truly new data, perhaps, not a test set anymore. And then we have to monitor it, maintain it, deploy it on small devices, if that's what we are doing, whatever else. Okay, so before I move on, I wanted to talk about what hyperparameters are, since I use this word here. At the beginning, I said what we are trying to do is to learn a function. And the way what learning a function means is we have a large family of functions, which is parameterized by many parameters, and we choose those parameters in a way that they fit the data we have. For example, if you want to do a polynomial fit, the parameters are the coefficients of the polynomial. The hyperparameters are properties of how we choose the model. So before we start training, we have to choose some hyperparameters. For example, if you're doing polynomial fitting, we choose manually which degree of polynomial should I use. And that's something that the experimenter chooses, is not learned automatically. So those are the hyperparameters. It could be the size of the neural network, what kind of activation function the neural network has, for example, the general structure of the network. Even choosing which model we want to use is a hyperparameter. Okay, hope to have clarified this. Very quickly, because I'm late, I want to talk about reproducibility in machine learning, because I know you had a lesson about reproducibility. In machine learning, there are some additional challenges because we have the whole data as well. So we need to make sure that our results are consistent for ethical reasons, because if we do research and we publish, we need to make sure that our data is reproducible, our results are reproducible. Also for scientific reasons, because you do an experiment, it works, and then you do it again and it doesn't work anymore. It's a source of big pain. So reproducibility is important. What are the possible sources of stochasticity? It could be that if you start with randomly initialized models, so that the initial parameters are chosen randomly, that's a source of stochasticity. The data set, you may be shuffling it between training and testing sets randomly, that's important, or you may be using subsets of data, you may be changing data because you've acquired some new ones, that's important. You may change the framework, which is the library that you're using, many other things depending on the specific model you have. So what you need to do is keep track of what hyperparameters you're using, which dataset you're using, which code you're using, and for that you have Git, you have version control, and other aspects related more to production and to deployment in the real world. There are some libraries like 1DB or Guild AI and MLflow, which I haven't written there, which do this job for you in principle. So you can keep track of the hyperparameters of the data. So you're doing version control on everything. And so when you run an experiment, and then it records the results for you. So when you run the experiment, you know everything. You know what the conditions of that experiment were. So it's essentially a bit like a lab book. So I wanted just to mention this. Of course, we could talk about this for a while. Finally, and this is going to bridge us to the next part, I want to introduce you to Scikit-learn. Scikit-learn is the Python library that we use for machine learning, except deep learning, I would say. So deep learning requires some more sophisticated tools because support for the GPU, for example, support for big data. So loading the data in a kind of sophisticated way because it doesn't all fit in memory. So deep learning is a bit aside. But for all the rest of machine learning, Scikit-learn is a very nice and very well maintained open source, of course, library for Python. What do we have? classification, regression, clustering. We've talked about them very briefly, but we will look into them for the whole day. Dimensionality reduction, I'll say a bit more about it later. Model selection is all the tools for testing, training, evaluating whether the model is working and how well it's working under different points of view. Pre-processing is everything that has to do with normalization. So those are the big 6 families where you have everything that you need. This is an overview of Scikit-learn, and you'll find this in the documentation of Scikit-learn, and it's kind of a really nice, useful cheat sheet that tells you which model. If you are new to machine learning, it tells you which model you should choose, what you should do. So you start from here and say, okay, how much data do we have? More than 50 samples. Well, if you don't have more than 50 samples, you're not going anywhere. So get more data. If you have more, then the question is, are we predicting a category? Then if we are predicting a category and we have labeled data, then it's classification, supervised classification. If we are predicting a category, but we don't have labeled data, so there is no expected outcome, then what we are doing is clustering. If we are predicting a quantity, is regression. If we are just looking at the data set and trying to find structure, that's dimensionality reduction. And then within each category, it also tells you, well, if you have the number of categories, the number of clusters, then you may want to use this specific algorithm, k-means. If not, then maybe this could work better. Same for classification. Some are more suited for if you have more data. Some are more suited if you have less data. Some are more for text data. So it's kind of, it gives you an idea of the general aspect of the landscape. All right, so I'm done with these slides. I will take questions, and then we move on to our clustering tutorial.
Okay, thank you. There was one question, but I'm not sure I understand completely the question, so maybe you will. How much dependable is machine learning, and is there a way to evaluate it?
No, this is actually a very important question. Is how much can you trust it, if I understand correctly?
Yeah, I understand.
Yeah. So this is a really nice question, actually. So the way we evaluate it normally is we have a training set and we have a test set, and we do our best to make sure that the test set is as similar as possible to the real world application that we will use. And then we sort of say, okay, if it works to this, if it gives us this accuracy on the test set and this precision, this recall on the test set, then we know that it will sort of work well in the real world as well. And this is kind of what you do when you do statistics as well, right? I'm really sorry because you probably now hear the hammering. I don't know, how bad is it, Thomas?
We can still hear you.
Oh my God, it's really terrible. Very unlucky. So what was I saying? So this is a bit like when you do statistics. We have the COVID tests. How do we know the accuracy of the COVID tests? Well, we try it on a bunch of people together with maybe a more precise method, and then we see in what fraction of cases it gives us false positive, true positive, false negative. So you would kind of do that, but it's a black box. And the fact that the machine learning model is a black box is a problem. It can, because sometimes you want to know why the model has chosen something. So, and if you have a huge neural network, well, the decision comes from it's an emergent phenomenon. So it's difficult to explain. And there are cases, there's also research on explainable machine learning. So there is a branch of machine learning which is like writing models that tell you also why they've chosen something. They give you like an intuitive sense of where in the data they looked at to make a decision, for example. this is important because, for example, the European Union now has a law that says that you have the right to an explanation whenever a decision is made on you personally. So if a bank decides not to give you a loan, for example, you have the right to know if this decision was taken automatically by an algorithm. You have the right to know why. And that's because, you know, the bank is allowed to decide on a loan based on your input, on your credit score, and so on. But it's not allowed to decide based on your race, for example, right? So you have the right to know where it was looking at.
Yeah, I think it's really important for ethical question and bias in machine learning algorithm. So
exactly. So it's a good question because the answer is not that easy, and yeah, and there's still research in this field.
Definitely. Thanks.
So, and also, in fact, talking about, because you guys are physicists, once I talked about machine learning with a physicist who was actually doing research on using deep learning for high energy physics, like detection of particles and stuff. And he was saying, yes, we are doing research on this, but there are a lot of people who are skeptical because it's a black box and you don't know what's happening inside when a decision is made. Okay, so I will now ask you to pull from the school repository. I made some changes yesterday and I added some data, so please pull. And then open your Python notebooks. And we are going to work on some code finally. I'm sorry for sort of boring you with this 50 minutes of lecture. I will start. So this is the school page, and then I will go into the folder called Machine Learning 1 or Machine Learning. I don't know if you renamed it yesterday. In here, you will find the data, but I will ask you not to open the notebooks. Instead, use a new notebook because I will be doing live coding. So I will type in the code as I do things. And if you follow on the notebook that already has the code in it, you're going to be bored to death because I will go slowly. So it's better if you type it yourself together with me because it gives you a better understanding. I will use this clustering empty notebook. You can also do that. And I will open this one for myself. All right, so here we are again. Clustering, what is clustering? We are in the situation where we are predicting a category, but we don't have any labeled data. So we are trying to figure out how the data would be split up in different categories, but without knowing a priori which categories we have. So the classical example in Scikit-learn is this one. We have the observation of many flowers. This is insane. The noise is insane. And for each flower, we have the length of the petal in centimeters, which we measure, and also the width of the petal. This is a classic data set that you will find in Scikit-learn as example data. Automatically finds these groups. I also did this a lot during my PhD, where I had spikes of neurons in lots of places, and I had to find the individual neuron. Okay, so and we go back to our machine learning pipeline, define the task, we've done it, it's a clustering task, get the data, and this is what we are going to do now. So there is data in the data folder, so I'm going to import pandas. That's the library that I think you've already used during the school before. So pandas is, so let's do data equals pandas dot read hf5. sorry, yeah, HDF. That's the function for reading the HDF data format, which is where the format that we have the data from. And you'll find cluster A data. That's the first data file we're going to use today in the data folder. I hope you find it. If you get a file not found error like this, that means you probably have the data elsewhere. You are not working in the folder where the data is. So the notebook is in the folder right above the data folder. Okay, so if I write the correct data name, then I will get the data. Then, okay, so what was the number 3? Get an overview. The overview is, for example, first of all, we want to know, sorry, just a second, how much data do we have? So data.shape, 502. So this means we have, typically we want in Scikit-learn, we want the data to be, you have every data point in the rows and every feature in the columns. So, so we have 500 data points and 2 features. I will now show you what this. So this is a toy data set. I'm using a toy data set because I really want to show you the weaknesses and the strength of clustering methods and how important the assumptions are. So that's quite important. So then the next step is let's plot it so we know what we are working with. So let's plot data. There are 2 variables called x1 and data x2. And I use matplotlib to plot them, which I have to import first. Okay, that's the result. So, okay, so we can tell that this is an easy clustering. So imagine this is the width of your petals. This is the length of your petals or whatever. This could be also X, Y directions. And we want to simply take, find the 2 separate locations of the points. For example, you have a group of people moving around in here and a group of people moving around in here, and you want to separate them. And if there are any new data points, then assign them to the group that you made. So to do this, we use an algorithm called k-means, which perhaps you have heard of, and is the one that we are here in the Scikit-learn map. So k-means is a very simple and classic clustering algorithm. So model equals. This is worth learning because scikit-learn models are always have the same syntax. First, you instantiate a class of the model, and then you use the methods fit or fit predict to actually learn from your data. So import, from scikit-learn.cluster import k-means. So model is going to be an instance of our k-means algorithm. And what we need here is the hyperparameters. So when we define the model, the definition of the class requires all the hyperparameters that we need. And those vary from model to model. In the case of k-means, the model requires the expected number of clusters. So we have to tell it what's the number of clusters that we have. Now, in some other machine learning, some other clustering algorithm will instead rely on the expected size of the cluster, the expected separation between clusters, but we have to make some assumptions. So here we cheat and we say, okay, we know what the number of clusters is. We say that we are looking for 2 clusters. We are separating this data into 2 classes. Okay, so I've defined the model, and then the model always has a fit method that takes the data in, and the data is going to be, as I said, columns and rows. So the rows, on the rows we have all the data points. Let me plot it for you. On the rows we have the data points, and on the columns we have the features x1 and x2. Okay, so then I run this, and I don't see anything, but internally the model has learned from the data. And now I have something called labels, which I can print. So what do we see here? A bunch of zeros and ones, seemingly random. What are they? These are for each data point from 0 to 499. We have a prediction on where this data point of the training set should go. Should it go in cluster 0 or cluster 1? So this is predicting that the first 3 go into cluster 0, the 4th one goes into cluster 1, and so on and so forth for all of them. And this could already be what we need. That's the prediction that we have. To show that it has worked, now we plot this. And I'm going to do this through a function. So let's define a function. View the data, which takes the data and the model. And then goes, okay, as a shorthand, we say the labels are model.labels. And then we do plt.scatter of data x1, data x2. So these are the 2 variables. And then the color is going to be the labels themselves. Sorry, but I did not expect the noise to be this bad. And I also want to choose a nice color map. Okay, so let's use this now to display data and model. I also would like maybe to make those a little smaller, the points a little smaller. So as you see, every point in the left group was colored in gray, and every data point in the right group was colored in green. So the model has successfully told apart the 2 groups of labels, the 2 groups of data points. So it has worked. Okay, now I will pause for a moment, and I will ask you to try doing the same with the other data. So you can go back, and instead of cluster A data, you can try cluster B data, cluster C data, and cluster D data. So these are all toy data sets, but they are different toy data sets. And you can see that the k-means model is going to perform better on some of them and fail on others of them. I'm aware that I haven't explained anything about how k-means works and what it does, but we will get into that. So I will leave 10 minutes at the end to really go into what are we actually doing? What is this? What are all right, so the exercise is try with the other data files. And I will take a 2 minutes break to let you do this. You can use the same code, so it shouldn't require very long. Good luck. All right. How did it work? So I'm briefly looking at what's happening in the channel. Thank you to those who are monitoring the channel. For me, it's a bit difficult to do both things at the same time, but now I have it on my other screen, so I will see. Somebody asked me to make the fonts bigger. I hope it's a bit better now. And there's an interesting question. So somebody got these zeros and ones the other way around. So that's a nice example of reproducibility problem. Of course, the colors also will get swapped because the colors depend on this value of 0 and 1. All right, so this is natural because we don't have labels, so we are not telling the computer this should be zeros and this should be ones. And where does the randomness come from? It comes from the initialization of the model. At the beginning, the model starts with a random state, and then it optimizes it. And that's why some people get one side of things and the others will get a different, the exact opposite. But it doesn't matter because you're just swapping zeros with ones. So if you want to make it reproducible, then you would have to fix the random seed. You know that with computers, the numbers are never random, entirely random. They are actually pseudo-random. And so you can make sure that the randomness is frozen and it will kind of be the same set of random numbers every time. And this is something that people can do and people actually do for reproducibility purposes. So what do you get with other data sets? The second data set is similar to the previous one. Right, somebody in the channel did it and showed the picture. The second data set is pretty similar. We have random blobs of Gaussian data. It's similar, but the separation between the two is not that sharp. And even as a human eye cannot tell, if, for example, if this specific data here belong to one cluster or the other. So to go fast, the result is like this. So it seems correct to me, but of course, yeah, there could be uncertainties like this. So for group C, somebody's saying that doesn't work. This is how group C looks like also to me. So it's not a problem. It's supposed to be, I mean, it's not supposed to be like that, but it's showing you that this specific clustering algorithm doesn't work well when you have the cluster that is wider than the separation between the two clusters. It doesn't converge properly. So now we know a weakness of this specific clustering algorithm, which is called k-means. And in a bit, I will tell you why it's like that. If I do it with D data, we see another of the we see another example of where this will not work. And the reason why it doesn't work here is that the separation boundary between the two clusters is a curved spline here. Whereas this algorithm can only separate the clusters linearly. So the separation between two clusters is always a straight line. So, I mean, looking at it like this doesn't work at all. This is a terrible clustering algorithm. And in fact, yes, it is one of the simplest ones. And I want to spend some time making understand why it doesn't work and why it works. Why is this important? I will insist now, and I will insist on this later as well. You should always know a little bit of the theory behind. You should know a little bit of the theory behind the algorithm that you're using, for at least two reasons. The first is that if you don't know, then you don't know how you should choose the hyperparameters. And the second one is, these are algorithms that were designed by someone, by a computer scientist, a mathematician, somebody who's, or maybe somebody, an engineer who was trying to find an application. They were designed with hypotheses in mind. In this case, for example, the hypothesis was you have a linear separation between the two clusters. This data set is not under this hypothesis. So we are making the mistake of trying to use it for something that it was not designed for. So yeah, that's just to say that we need to know a bit of the theory behind the algorithms in order to make sure that we are under the hypothesis. So let me briefly explain to you how the k-means algorithm works. I like it because it's simple. I find it a very cute algorithm that works, in fact, quite well, and is sort of magic. So what's the maths behind it? It's not really maths. Suppose that you have the data that is looking like this. So you clearly have two groups separated by a gap here. Of course, this is relative. We could decide that, in fact, this is a third group. That's up to us to evaluate what we should be doing based on what the data means and what we are trying to do with it. So suppose that we are under the hypothesis that there are two clusters. So we are actually doing two means because the k is meant to indicate the number of clusters. So the first thing that we do is we place two centers, the cluster centers, the hypothetical candidate cluster centers, we place them on two random data points. And this is the source of randomness. This is why you saw different results. Okay, so we place them in two random places. Then we cut the space in two, and we assign the ones that are closer to this center. We assign them to this center, and we say, okay, this is one candidate cluster. Then we take the ones that are closest to this center, and we say that's the other candidate cluster. Okay, that's the second step. Third step, move the center to the center of mass of the data points colored in the same way. So the ones that were said to be belonging to that cluster, right? So the data point of the center of mass of the yellow ones is about here. The data point, the center of mass of the orange one is about here. And then I update, so I go back. That's a for loop. I go back and I again decide the ones that are nearest to this center go to this center. The ones that are nearest to this center go to this center. And in this case, the color of this one has changed. So I repeat this assignment. And then again, I move the centers again to the new center of mass, which has slightly updated because this thing changed color. Okay, and then I repeat again and again and again. And in this case, I move again the center of mass, and I attribute again the points to the cluster. That's the next step. So the algorithm now has converged. Because if I repeat it again, no data points will change cluster. So it has converged to a stable point, and that's the solution. So that's how k-means works. Any questions?
Sorry. Yes, there is one question. Is it possible that a machine learning algorithm is so complicated that the people applying it don't really know how the result came to be? And I think that's something you answered.
Yeah, I talked about it earlier. It happens quite a bit. And the cool thing is that that's really the point of machine learning, is when we don't know how to explain how we tell that a cat is a cat, and therefore we can only learn it by example and let the computer automatically figure out the features. So it's always going to be a bit like that. Okay, so we have 10 more minutes on the clustering. I'm sorry I rushed through it a little bit. Let's talk about a couple of other things. First of all, let's try what happens with 3 clusters. So in this data set, well, of course, it's terrible. let's go back maybe to the second data set, so B, and I show you what happens with 3 clusters. As you see, the result looks kind of reasonable, in fact, but that's an optical illusion because we know that there are 2 clusters in here. There's this blob and this blob. But I'm just telling that this is a hyperparameter. Changing the hyperparameter can change the result quite significantly. And evaluating the model with our own eyes sometimes can fool us into thinking this is better than another. So choosing the hyperparameters carefully is important. And especially choosing an evaluation strategy is important. Possibly doing it before you you actually run it. So you should have, at the beginning, you should have an evaluation strategy. For clustering, it's not easy to say how do you evaluate it because it's unsupervised. And it would depend a lot on what you're actually trying to do. Okay, so going back to our terrible D dataset, we said this doesn't work at all. We also saw that the C dataset didn't work at all. And I said 2 reasons. One of them is that it doesn't work well when the spread of the cluster is larger than the distance between clusters. And the second one is when the separation between clusters is not a straight line. For this one, for the first one, maybe you'll have an intuitive understanding of why that happens. The convergence is not guaranteed to converge with the 2 cluster centers. So if you at the beginning initialize the cluster centers on the same cluster, it's very easy that you'll get this stupid vertical split. So it doesn't converge properly, and it's sort of a problem of the algorithm. But this one is a case where really you are not in the hypothesis of the algorithm, because as I've explained, you're always looking at what's nearest to this cluster and what's nearest to that cluster. So what you get is always a straight line separation. You cannot have concave clusters. They're always convex in k-means. And so here it's never going to work. So what do we do if it doesn't work? There are many other clustering algorithms that we can try. This picture comes from the documentation of Scikit-learn itself. And here's the zoo of possible models that we have. So that's k-means, and that's on a number of example data sets. So we see that it works pretty well in this case. It works okay in this case. It works very bad when we have the wrong number of, so the wrong hyperparameter, the wrong number of clusters. And it works really terrible when we have non-convex clusters. So I don't know the details about them all, but I can tell you about some of them. As you can see, some of them perform better in some situations, some in other situations. I know a bit about MinShift because I used it a lot. MinShift essentially works by every data point looking into a neighborhood and then moving towards a local maximum of density of the data points themselves. So there's sort of an accumulation to local maxima of density. So it works very well in this kind of case here, of course, in this one. And it also figures out the number of clusters by itself. So in this case, it says this is only one cluster. But it still doesn't work. The separation is still linear and it still doesn't work well in this kind of cases. dbScan, to give another example, works sort of the opposite. It looks at the white space between clusters and uses that to say, okay, that's the delimitation between clusters. So it doesn't work well in a situation where 2 clusters are very near, like here. It does work well in this case, this case, this case, and it also works really well on concave clusters and overlapping clusters. Sorry, one inside the other. So dbScan is a very nice general purpose algorithm. Among more specific ones, instead, we have the Gaussian mixture. Gaussian mixture does exactly what you think it does. It fits a sum of Gaussians. So it assumes that the probability distribution of data point positions is Gaussian. And it fits a sum of Gaussians on the dataset. So when the dataset is a sum of blobs, like here and like here, this is the best, although it's a bit slow, and here as well. When the data is not Gaussian, because it's not round blobs, it works terrible, again, here. And when the data is not statistically Gaussian, because this is uniformly distributed, it also works really terrible. So this image is in the Scikit-learn documentation. As I said, Scikit-learn also has a lot of tutorials, and you can always, it has a very friendly reference and also a friendly community. So you can always look at what's the best algorithm for my purpose in this sort of way. Finally, we have a couple more minutes. Let's do another exercise. So we said this is bad. This is a bad data set for k-means. So I will give you actually a couple of options. You can choose your own exercises. You can either try on the D data, so the difficult one, try using another algorithm, which is called scikit-learn.manifold.tsni. So this is a non-linear data set. No, sorry, what am I saying? Not tsni. Use dbscan, scikit-learn.cluster.dbscan. I'm already thinking about the next lesson. And you should see that this works. Alternatively, you can try 3-dimensional data. So far, I've given you only 2-dimensional data, but in most cases, we are going to use 60-dimensional data. What, you know, it could be anything. And maybe that, yeah, I should have maybe shown you. It's I used 2-dimensional just to visualize, but that's an unfair assumption. You could do it with any kind of data. So there's actually 3-dimensional data in data cluster 3D data.hf5. F5, and this has 3 clusters in it. And you have to come up with your own way of visualizing 3D data. The last exercise, which you are definitely not going to do today, but maybe for the future, if you like, it's like a bold idea to understand the theory behind it. So if you are more of a theoretical kind of person, try re-implementing k-means from scratch. So you can choose one of these 3 exercises and do it in the next, choose one of the first 2 exercises and do it in the next 5 minutes. And then we have the coffee break. I will be here for another few minutes to answer questions. And other than that, if you are done, if you're happy, feel free to go for your coffee. Okay, so while you do this, I will answer some questions. Somebody's asking, how do we choose how does the algorithm choose the line that cuts through, that separates the 2? It depends on the algorithm. In the case of k-means, what is chosen is actually the cluster center, as I showed in the slides. And the line is simply the line that divides the points closest to this cluster center from the points closest to that other cluster center. So you measure the Euclidean distances between between the data points and the cluster centers, and you divide by which is closest to which. That's the case of k-means specifically. Later, we will see another algorithm that decides in a different way. Not for clustering, for classification. Somebody saying the model C should randomly fail depending on the first selected data point. Maybe not. It could also be that it really converges to the wrong solution. That was the case where you have the two wide horizontal clusters which were cut vertically instead of horizontally. Yeah, it could be that it's not random, that in fact it really converges to the wrong solution because of the width of these clusters. Another important question is, how do we choose the correct hyperparameter? So this is a very important question, but it's difficult to answer it in general. For the case of k-means, you are supposed to know the number of clusters. That's the assumption of the model. If you don't know, either you guess or you use a different algorithm. For other models, so in general for machine learning, choosing hyperparameters really is the part where you need a scientist that tries and figures it out. How do you do it in general? You would set up an evaluation structure. So you would have to know, based on what do I judge whether the model is working well or not, okay? So then you have a validation routine that says, this is a good model, this is a bad model. And then you try for different values of the hyperparameter and say, okay, this value of the hyperparameter works better. That's one way. So it's sort of a trial and error way. The other way is if you have a theoretical reason why you want the hyperparameter to have precisely a value. And that would depend specifically on what the hyperparameter is in that case. But generally speaking, sometimes we don't know, sometimes we have to try. And that's where really the wisdom of the machine learning scientist goes in. You have to set up a proper evaluation routine that doesn't have biases in it, and based on the results on the validation set or doing cross-validation, you will figure it out. So this is called model selection. So choosing the correct model, choosing the correct hyperparameters based on the results on a certain testing routine. And Claudia is going to talk about this more extensively in the afternoon. Yeah, so other questions also revolve around things like, again, how do we choose the number of clusters? I think I've already answered. You should know it. If you don't know it, you either use a different algorithm or you, again, have an evaluation routine that says this is looking all right, this is looking bad, and then you try to guess. Did anybody try the 3D data and wants to show the result? Ah, yes, somebody did actually. I hope you don't mind if I show everybody your results. I think this one is, if I understand correctly, this is the 3D data, right? But something didn't go very well, I think, if that's the 3D data. There should be 3 clusters, not 4. And maybe the display here of it's difficult to find the right way of looking at the dataset to show that there are 3 clusters. However, I will give you later the link to the UC Irvine lesson where I took this example from, and you will have all the codes to display it and to show how it looks like. This, on the other hand, is probably dbScan or another learning algorithm used on this data, and that worked out very well. So I will show you the result on the 3D data, how it should look like as it was made in the original lesson. So this is what you guys got right now. If you look at it from the X, Y, or Z axis, it looks very messy. But the author of the data knew the right rotation. And if you rotate it, you will see that, in fact, there are three different there are three clusters which are very well separated from each other, and k-means does work. It separates them properly, as you can see here. But the problem here, so the problem in the result you got, Thomas also got it, and Daniel Egbo got it. It looks wrong, but it's not wrong. K-means did a good job. What doesn't look right is the way we are looking at it, because it's 3D, so it's difficult to display it. Okay, if there are no more questions, I will stop here. In fact, I hope that some of you are already enjoying their coffees.
Yeah, thank you, Martino. Very nice live session to start this day. And I think, yeah, many people followed and yeah, we saw many picture in the chat, some funnier than others. During this coffee break, we also have a virtual group picture if you want in GatherTown. So everybody that want to participate, please join in GatherTown. We will join in the main hall with the grass. If you can find that, it's on the right in GatherTown, and we do the group picture in maybe 5-10 minutes to leave some time for people to join. And we resume the lecture at 11 o'clock.
Okay, thank you everybody for coming, and see you in a bit. And again, sorry for the noises.
It's fine. Like that with homework.